introduce the idea of limit at a point. Here are the main points that we address in the video. Please read these and think about them carefully as you watch the video. A limit exists at a point if it is possible to approximate the value of a function or a hole in the function as accurately as desired. Better approximations to the limit can be found by finding overestimates and underestimates which are closer to one another. The error is less than or equal to the difference between an overestimate and an underestimate. Here's a function of f of x equals to 12 times x over 2 to the 1 over x minus 2 power, minus 16. And here's a graph of this function. If you look at closer at the formula, you'll notice that the exponent has a fraction that is undefined at x equals 2. This causes the entire function to be undefined at x equals 2. Let's look at the graph carefully at x equals 2. Since f is undefined at x equals 2, the graph f has a hole when x equals 2. Since we know the x value of this hole, we ask what is the precise height of the hole. We can indicate this unknown value of y-axis. It looks like this value is roughly 3.8 units. If we were to zoom in, we could better estimate the height of this hole, but it will still be an estimate. Instead of zooming in immediately, let's look at a systematic way to find the height of the hole as accurately as desired. This precise value is noted by the following notation. This notation is read as the limit as x approaches 2 of f of x. So the precise height of the hole is value of the limit. This limit exists if it's possible to approximate the height of the hole using f as accurately as desired. So let's find this value as accurately as desired. Say we want to estimate the height of the hole within 0.01 of the actual value. To start, we'll find an overestimate of the height of the hole. We can see that f is decreasing, so evaluating f using value of x less than 2 will yield overestimates to the height of the hole. So let's pick x equals 1.5. The length of this green line segment is f of 1.5. And when we evaluate f at 1.5, we get 5.333. So the value of our overestimate is 5.333. To determine how far off our estimate is from the actual value, we can consider the error for the overestimate. That is the difference between the overestimate and the actual height of the hole. But since the actual height of the hole is unknown, the size of error is unknown. On a graph, we can label the error as the vertical distance between the height of the hole and the overestimate. By looking at the y-axis, it is pretty obvious that the length of this red line segment is greater than 0.01 units. So instead of picking a value for x far away from 2, let's pick a value for x that is closer to 2. Let's move x closer to 2. So now the value of x is 1.99. The overestimate is now f of 1.99. When we evaluate f at 1.99, we get 3.809. Since the error is not even really visible on the graph, we might think that overestimate may not may now be within 0.01 of the actual value. Let's zoom in on the graph to better see the error. Since we do not know the actual value of the height of the hole, even though our approximation is better, we don't know for sure if the error is less than 0.01. So how do we guarantee an estimate is within 0.01 of the actual value? If we find an underestimate of the height of the hole, then the difference between over and underestimate is shown by length of this orange line segment. This length of the orange segment is at least as large as the length of the red segment, which is to say that the error for the overestimate is less than or equal to the difference between the overestimate and underestimate. So if we make the difference, if we make this difference between the over and underestimate less than 0.01, then the error for the overestimate will also be less than 0.01. For our underestimate, let's use f evaluated at 2.01, which is 3.76. So the error in using either of these approximations is less than or equal to the difference between the value of overestimate and the value of underestimate, which is equal to 0.049. But this difference is greater than 0.01. Thus, we're not guaranteed that our approximation is within 0.01 of the actual height of the hole. So let's make the values of x closer to 2. We'll stop once the difference between the overestimate and underestimate is less than 0.01. Now the overestimate is equal to 3.789 and the underestimate is equal to 3.78. So the difference between the overestimate and underestimate is 0.009, which is less than 0.01. So any approximation of the height of the hole between 3.78 and 3.789 is within 0.01 of the actual value. So now we found an estimate of the height of the hole, but our main goal was to think about the limits. So what is a limit? We already stated that the limit exists if it is possible to approximate the heights of the hole using f as accurately as desired. I gave an example for finding approximations accurately to within 0.01 of the actual value. But we could find an approximation within 0.005 of the actual value. Or we could find an approximation within 0.0001 of the actual value. Or we can make the error as small as we like. So small that overestimate and underestimate become virtually indistinguishable. When this happens, the value that the approximations approach is the value of the limit. So this is what a limit is. It is the value that the overestimate and underestimate both approach as we approximate the height of the hole as accurately as desired. And in this example, to 3 decimal places, the value of limit as approaches 2 of f of x is 3.785.